Okay, thank you. Our next speaker is Justin Wilgus from the University of New Mexico.
All right, hi. I'm excited to be talking to you about the work we've been doing using shear wave velocities to image the upper crustal magma storage beneath Valles Caldera. Valles is one of three major silicic continental systems in the western US and is located in northern New Mexico. And it's a fairly impressive feature. I'm showing here an aerial photo from the north looking south, and it's approximately 20 kilometers across. The dashed line is the topographic rim of the caldera. The resurgent dome is outlined here in the center, Redondo Peak, and then the solid white lines are smaller, younger volcanic centers that have erupted after the most recent calderic forming eruption. And this is work I've done in collaboration with colleagues at the University of New Mexico, University of Illinois, Australia National University, and University of Texas, El Paso. So here I'm just showing a schematic diagram of the structural evolution and anatomy of a caldera system. In A, we have before calderic eruption. In B, I'm showing immediately following eruption, where so much material is ejected that the roof of the chamber actually collapses in on itself. And then you have these outflows of these ignimbrite deposits and increased structural complexity generally. And then in C, I'm showing after eruption, where you have uplift of the resurgent dome, and then more moderate magmatism and volcanic eruptions on the flank of the resurgent dome, but still within the calderic ring fracture or the topographic caldera rim. And Valles is actually sort of a geologically iconic feature, as it's a type locality for this type of eruption. And so we have fairly detailed geologic records for the caldera forming processes from geology that's done at the surface. But large uncertainties remain regarding the contemporary state of the underlying magmatic systems. And furthermore, geochemical and petrologic studies are showing that these types of systems can actually host diverse life cycles and have a variety of hazardous eruptive scenarios. So the most recent caldera forming eruption at Valles Caldera occurred 1.2 million years ago, and it helped shape the modern topography that I'm showing here on the right, and also erupted the Bandelier Tuff. That's this tan shaded regions on the flank of the caldera, and formed the most recent caldera ring fracture fault outlined with these black dotted lines. The green dotted line is a 350 C per kilometer geotherm, which was defined by measurements from the boreholes, which are each of these black squares. And then there's numerous smaller secondary eruptions that have occurred within the caldera, topographic caldera, from red to yellow, decreasing in age. The youngest being Banco Bonito, that's this yellow area, at 68,000, it's been dated at 68,000 years old. And it's near this region of high heat flow, which is suggestive that there might be potential recharge occurring. So there's been a previous P-wave tomography study that was conducted in 1998 by Steck et al., and they found this low velocity anomaly localized in the crust below Redondo Peak. But there's no shear wave velocity images that have been or studies that have been conducted at Valles Caldera. So the goal with this project was to get shear wave velocity structures to help improve the constraints on the presence, the depth interval, and the melt content in the contemporary magmatic system, help determine the modern caldera cycle stage, and place Valles in the context of the other major silicic calderas that I've mentioned in the western US at least, and then identify the potential hazards at a local to regional scales. So to get at these motivating questions, we deployed 97 3-component 5 Hertz nodal seismometers in and here's one of those seismometers I'm showing here is a screwdriver for scale. You can fit quite a number of these in your backpack and get moving pretty easily. So 71 kilometers is the transect length, and they have each one of these triangles is one of those seismometers, and we space them at 750 meters apart. So we source Rayleigh wave arrival times from seismic ambient noise. So the ocean is constantly undergoing these sort of pressure waves, and they couple with the ocean bottom. And between two seismometers, you can sort of record this weak background signal, and through cross correlation, it removes the sort of non-coherent arrivals and boosts the signal noise ratio of the coherent arrivals. And then you can get an arrival time of a surface wave. And that's just an example I'm showing down here in this schematic. And over here on the right, I'm showing the results from our vertical noise correlations. This is a stacked distance versus time image of all of those within our study, filtered 3 to 9 second period. And what you can see is that there's pretty high quality for these nodal data, and that there's a Rayleigh wave move out of approximately 3 kilometers per second. That's that blue dashed line here. Another advantage of this study is that each seismometer can work as a source and a receiver. And so here down in the right, I'm just showing a virtual source and a move out. And then what you can see is that as that Rayleigh wave energy enters the caldera ring fracture, there's a strong delay in the arrival times. And this is about as close to a direct observation as you can get when you're working with ambient noise cross correlations. So from there, for our phase velocity tomography images, we use a damped least square straight ray inversion for phase velocities. This is a pseudo cross section. So on the y-axis is period. Each period is sensitive to a broad range of depths. And what stands out immediately is a significant localized low velocity zone between 3 to 5 second period. And that's within the ring fracture below Valles Caldera itself. And from those phase velocity images, we could use each one of those points as an input into an inversion for shear velocity tomography. For this, we use a Monte Carlo Markov chain inversion with 9 parameters in total. And so our results here show this significant low velocity zone, approximately 6 kilometers wide and a 3 to 10 kilometers depth range. And if we were just to take the volume below 2.1 kilometers per second, this would, and look at that relative to the rest of the velocity, shear wave velocity, it would indicate a 32% reduction in velocity, which becomes pretty difficult to describe without conjuring fluids or volatiles or melt of some sort. I would say that this is a fairly sharp gradient on each side of this anomaly, and some of that has to do with the inversion that we're using, which is run on each point along this transect, and I'm showing that here in the misfit values. So resolving that steep gradient within a small area is somehow artificially creating a sharp contrast, although we do think it is fairly sharp, maybe not as sharp as imaged here. And so with our shear wave velocity, since it's sensitive to melt, we could do some geochemical modeling to get an estimate of melt percent. For this, we use a rock from the Banco Bonito rhyolite, and the purple X is a phase equilibrium model to recover the elastic properties of the rock. And then from there, we use an effective medium theorem to determine elastic properties of the multi-phase materials that are present. To do this, we use elastic C. And in particular, we're interested in this aspect ratio, which is the geometry of the pore space of the melt pockets. So we vary the aspect ratio between 0.1 and 0.15, which is textural equilibrium, and intersecting that with our shear velocity estimates, we get a result of 17 to 22% melt range. And I should say that this is similar to some results that colleagues have done in Yellowstone, both in structure with VS below 2.2 kilometers per second at 5 kilometers depth, and then also with the percent melt, 16 to 20%, but this would be at a larger volume. So could be in a different stage of the life cycle. And so just putting that into context of the Valles magmatic system, the depth range of the anomaly overlays this petrologically estimated stored depths, 2.5 to 9 kilometers. And so then we can estimate volume from there, really back of the envelope, since we only have 2D results. This would give us 40 cubic kilometers, assuming a 20% melt fraction. And so only a small fraction of this volume would need to mobilize to produce volumes consistent with the most recent Banco Bonito eruption. So our results, 6 kilometer wide, low velocity anomaly below 2.1 kilometers per second within the caldera's ring fracture at 3 to 10 kilometers depth. 17 to 22% rhyolitic melt may be present. The presence of this melt, just a key takeaway, it doesn't necessitate an eruption. So this question of eruptibility is still outstanding. The magma body could be a stable cooling reservoir. If recharge is occurring, is likely for a smaller non-calderic eruption. And with that, I'll take any questions or you can email me.
I'm really sorry, Justin, but we do have to move on in the interest of time. But if you have questions for Justin, I'm sure you can track him down at some other point in the meeting.